Okay, so we'll study fluids and pressure. That's what this chapter covers. Your body's fluids has many fluids. You transport, you pump blood all over the body that carries oxygen and nutrition and nutrients and stuff like that. And to make fluid flow, you need a pressure difference between the ends of a tube. Okay? So when you go to the doctor's office, one of the first things they measure is pressure, your blood pressure and stuff like that. Okay, if the pressures are wrong, then it's an indication of that something is wrong. Okay, so it's an important thing that they measure. Okay, so we'll study fluids and pressure. Okay, here's a quote by Richard Feynman. He says, "If you thought that science was certain, well, that is just an error on your part." Okay, so science is a lot of trial and error. Okay. And you start with a lot of approximations. Okay. So let's define pressure. Pressure, denoted by P, is force per unit area. Okay. So for instance, let's see here. Okay. So this diagram illustrates. So let's say you push on this arm with a force of 10 pounds. And you push the needle with a force of 10 pounds. The force is the same in both cases, but obviously this force here, the result is different. Okay? And why is that? Because this force is applied in a small area and the pressure is greater. See, the pressure is force divided by area. And here, the needle is applying a force on a smaller area, the pressure is greater, and that greater pressure will break your skin. Okay? So pressure is defined as force per unit area. Okay, so here are some places. A record player needle exerts pressure on a record. Water near the bottom of a swimming pool exerts noticeable pressure on a swimmer's eardrums. Okay, so what that means is, what they're saying is, and you'll learn this. Okay, so when you're walking around, the pressure in your eardrums is 1 atmosphere. Yeah? And if you're swimming underwater, you will learn if you're 10 meters underwater, the pressure now is 2 atmospheres. Okay, so you'll notice the pressure on your eardrums. So you have to balance the inside pressure in your middle ear. Okay, otherwise your eardrums is being pushed. Okay, so that's what we mean here. And the 10 meters is 33 feet actually. So it is roughly twice the height of this ceiling. Okay, that's 10 meters. And atmospheric pressure changes with weather. Okay. Now the units of pressure forces are measured in newtons, area in meter square. These are SI units. So the units of pressure are Newton meter square. And this combination of units is called a Pascal, after Mr. Pascal. Okay. So the SI units for pressure are pascals. Okay. 1 atmosphere, so here are some numbers that you want to be familiar with that you will see in the medical field. Okay, 1 atmosphere is 10 to the power 5 Newton meter square. Okay, so that's 100,000 Newton meter square. You will also see PSI, which is what you see when you fill your car with air, car tires with air. Okay, 1 atmosphere is 15 pounds per inch square. That's what PSI means. Okay, so PSI is pounds per square inch. So 1 atmosphere is about 15 pounds per square inch. Okay. In blood pressure measurements, you hear your blood pressure is 120 by 80, normal blood pressure. What does that mean? That's in millimeters of mercury. Okay, so 1 atmosphere is 76 centimeters, which is 760 millimeters of mercury. Okay. So this is also 760 millimeter of mercury. Okay. And we'll come to that in a bit as well. 1 atmosphere is also 10 meters of water. Okay. I don't know if you guys are familiar with CPAP machines, or and there the pressure adjustment is about 10 centimeters of water. Okay, so that's about 0.1% of the atmosphere. Okay? So CPAP machines, what they do is for people when they sleep at night, their air tubes collapse. So you have a machine that pumps air at a higher pressure, 1.1%, 1.0. Okay. So it's 0.1% of the atmosphere. So 1.001 atmospheres. So it pumps air at a slightly higher pressure to keep your air pipes open. Okay? So anyway, 1 atmosphere is 10 meters of water. So twice this height of the room, that a 33 feet column of water will exert 1 atmosphere. Okay? So for instance, that means if you go diving and if you're 33 feet underwater, now you have to breathe air at 2 atmospheres. Okay? If you're 66 feet underwater, you have to breathe air at 3 atmospheres. Okay? All right, so you want to be familiar with these numbers. Okay, 1 atmosphere is 10 to the power 5 Newton per meter square, 10 to the power 5 pascals. 1 atmosphere is 15 pounds per square inch. 1 atmosphere is 760 millimeters of mercury, and 1 atmosphere is 10 meters of water. Okay. All right, so we saw that pressure is force per unit area. So you apply the same force with these 2 devices, and you feel the difference. That's because when you're applying here, the pressure is higher. So if someone pokes you in the arm with a finger, you will feel it. If they poke you with a hypodermic needle using the same force, the needle penetrates your skin because the higher pressure breaks your skin. Okay. Fluids as well as solids can exert pressure. Okay, so all right, so what is this pressure? So an atmospheric pressure is 10 to the power 5, I'm calling this 1. It's 10 to the power 5 Newton per meter square at sea level. What this means is, so if you're at sea level, if you take a 1 meter cross section, so that's 1 meter by 1 meter, 1 meter by 1 meter is about this much. Okay? And if this column of air all the way to space, the weight of this column of air all the way to space is 10 to the power 5 newtons. Okay. Weight is mg mass times gravity. Gravity is about 10 meters per second square. So if you divide that by 10, the mass of this column of air all the way to space is 10 to the power 4 kgs. 10,000 kgs. Yep. Okay. 10,000 kg is the weight of a school bus. Okay, so this much air all the way to space weighs as much as a school bus. All right, roughly your surface area is about that. So there's a school bus sitting on it. So why aren't you getting crushed? Okay, so let me show you another example. Here, can I have a piece of paper? Okay, so you saw that atmospheric pressure is 15 psi, 15 pounds per square inch. So this is 10 inches by 10 inches. That's 100 square inches. So the force of the air on this thing is 15 times 100. 1,500 pounds. 1,500 pounds. That's the weight of 10 people. How the heck isn't this flying off? So atmospheric pressure is large. You guys understand what I'm saying? Okay, so 1,500 pounds of force. And that's because there's an exact 1,500 pound force here. That's why you're not collapsing. You're breathing, the air you're breathing is at 1 atmosphere in your lungs. Again, that's pushing back. So when you go diving, and if you're 33 feet underwater, the pressure on you is 2 atmospheres. And so you have to breathe air at 2 atmospheres. Okay. So again, the pressure, what this means is, so 10 to the power of 5 newtons, that's the weight of this column of air all the way to space. Okay. And so now you guys understand that if you go to a higher elevation, the pressure decreases because that's the weight of that column of air. Okay. And in fact, if you go up 5 miles, the pressure decreases to half an atmosphere. Okay. Okay, this illustrates this large, the magnitude of the pressure. So on this wall, okay, the pressure of air exerts a force in this direction. Okay. And so this problem calculates how large this force is. Okay. So the force on the side of the wall is, the area is 10 meters square. Okay, so it's 10 meters square. You can think of 3 meters by 3 meters. So roughly half that wall. Okay, we'll calculate the force on half that wall on the side there. Okay, and so pressure is force divided by area. So force is pressure times area. Okay. So the pressure is 1 atmosphere, which is that, and there's the area. So the force is 10 to the power of 6 newtons. Okay, 10 to the power of 6 newtons. So your weight is about 500 newtons. 10 to the power of 6 newtons divided by 500 newtons is so 10 to the 3 times 1,000 divided by 500 equal to 2,000 people. Okay, so the force on this wall is equal to the weight of 2,000 people. And the reason the wall is not falling down is because there's an equal and opposite force on the other side. Okay. So we live in Florida. We encounter hurricanes a lot. Okay. Now you will learn toward the end of this chapter, in the latter half of the chapter, when fluid moves, when you have hurricane force winds, when the air moves, the pressure drops. Okay. So if there's a lower pressure on the top, the air inside the house is not moving. That's still at 1 atmospheric pressure, and it'll exert a large force on the roof, and that's how the roofs get blown away. Okay. All right. So so during hurricanes and tornadoes, you have to worry about this, the effect of this pressure. All right. So we said pressure is due to the weight of this column of air. Okay, here's a microscopic view of pressure. Okay, and you want to. So what is atmospheric pressure in PSI? What did we say is atmospheric pressure in PSI? I'm sorry? No, that's the SI unit. What's the value for 15 psi. Okay, so in your car tires, what is the pressure? About 32 psi. Okay, so we'll see that that's roughly 2 atmospheres. We'll see that's something called gauge pressure, but we'll come to that in a little bit. Okay. So here's another way to look at pressure. Here's a microscopic view of pressure. All right, so you can see that. So there's this gas in this container, and the pressure is 30 atmospheres. That's a very large pressure. Okay, and so let's say that's 30 atmospheres. So 1 atmosphere is 15 psi. 30 atmospheres would be 450 psi. 30 atmosphere on 1 square inch, you would have a force of 450 pounds. That's the weight of 3 people. Okay, that's an enormous pressure. And how's that pressure being exerted? It's these air molecules bouncing off the walls that are exerting the force. Air molecules that are tiny. Yep. And so billions of those collisions are happening every second. Okay? So that's how pressure is being exerted. All right, in this coffee cup, the liquid molecules are bouncing off the walls and they're exerting pressure as well. Okay? So that's here is a microscopic view of pressure. Okay, and you want to keep that in mind. All right, so that's what's illustrated here. When an air molecule bounces off or a fluid molecule bounces off, the wall is exerting a force on the atom, and the reaction force exerted by the molecule on the wall is what's causing the pressure. Okay, so gas in a container exert pressure on the walls. This pressure is caused by the collisions of molecules with the walls. Many billions of molecules strike the wall every second and thereby exert a nearly constant average force on it. All right, so here is the ideal gas law. So going back to that. Okay, so here, that's the volume of the container. There's the temperature. There's the pressure. Okay, and this is the amount of gas in there. Okay, now what I'll do is I'll increase the amount of gas in there and watch. Okay, I'm going to increase the amount of gas and watch what happens to the pressure. I'm keeping the temperature the same. I'm keeping the volume the same. Okay, I'm going to increase the amount of gas, and the pressure you'll see is increasing. Okay. Why did the pressure increase when I increased the amount of gas? I'm sorry? There's more particles, and what did they do? More are hitting the walls, and so the pressure increased. Okay, and more are bouncing off the walls, and so this law illustrates all of that. This is the pressure, that's the volume of the gas, and little n is the number of moles of gas, r is the gas constant, and there's the temperature. Okay, so what we did was we increased the number of gas molecules, and hence the pressure increased. We kept everything else the same. Okay, kept the volume of the containers the same and the temperature the same. Okay, so this is the ideal gas law, which gives you the relationship between pressure, volume, and temperature for a gas.
What is the R?
R is the gas constant. Okay. And its value is 8.314 Newton Kelvin per mole. I gotta figure. Yeah. Okay.
Is that the constant?
Yeah, that's a constant. Mm-hmm. All right. So, I'm sorry?
You
So when you do chemistry, you'll use that a lot. All right. So we saw that what was atmospheric pressure? That that was the weight of this column of air all the way to space. Okay. So now let's go underwater. So let's say you're here. Now what is the weight sitting on you? There's the column of air sitting on you, and then there's this column of water sitting on you. Okay, so if you were here on the surface, the pressure is atmospheric pressure on you. Just the weight of the column of air. So you go deeper in the water, now the weight of the water adds on. Okay, so the pressure on you at this depth is the atmospheric pressure plus the pressure due to the column of water. And it turns out that, so this is the density of the water, this is density of water, that's acceleration, acceleration due to gravity, and that's the depth at which you are. And it turns out that if you're at a depth of 33 feet or 10 meters, this will become equal to P naught, will be 1 atmosphere. If you are at a depth of 66 feet or 20 meters, that's 2 atmospheres.
For that 33, it's 1.
I'm sorry?
For that 33 feet, it's
Yeah,
1.
it's 1 atmosphere. At 66 feet, it's 2 atmospheres. Okay? So if you're diving at 66 feet, now you're having to breathe air at 3 atmospheres. Okay? Now when you breathe air at a higher pressure, that air, more air dissolves in your blood, and if you come up too fast, that air will bubble, and if bubbles form in your joints, get trapped in your joints, those are the bends. It hurts. Okay? So if you're diving, you have to come up slowly so that the air dissolved in your blood doesn't bubble. Okay.
So the atmospheric pressure is just the weight of that column alone.
Yep. Okay, so pressure is, you can think of it as, so there's 2 ways of thinking of the pressure. Microscopically, it's all those molecules bouncing off the walls, okay, off a surface. Or you can think of the weight of this column of whatever is sitting on top of you. Okay? So for instance, its pressure is force divided by area. Right now the pressure is 1 atmosphere here on the table. And now I increase the pressure if I push down on it. Okay? All right. What is 1 atmosphere in mercuries? In height of Mercury? We mentioned that? Very good. 760 atmosphere. 760 millimeters of mercury. All right. In a lot of the medical field, in a lot of situations, what we do is we actually talk about gauge pressure. Okay? And the reason it's called gauge pressure is because most gauges measure that. What they measure is not the actual pressure, but the actual pressure minus atmospheric pressure. Okay? So that's so when you say your pressure is 120 millimeters of mercury, this is what is being measured. So the actual pressure of the blood is P equal to P naught plus 120 millimeter of mercury. And P naught is 760, so the actual pressure is 760 plus 120 equal to 880 millimeter of mercury. Did you guys understand that? So the gauge pressure, so we define a gauge pressure because that's what most gauges measure, is the actual pressure, absolute pressure, minus atmospheric pressure. Okay? And so keep that in mind. Every time we say a pressure, it's really gauge pressure that we're talking about. Okay? So in the medical field. All right, and here's the reason why we're talking about this. Okay. All right, so let's say, well, we can talk about your eyeball. So inside your eye, the fluid is under higher pressure. Okay. Okay, so what is the pressure here? 1 atmosphere. What is the pressure here? 1 atmosphere. Now, if I increase the force slightly, that thing bends. Okay. So how do I keep it from getting pushed? So in a balloon, for instance, the pressure is higher, and that's why the balloon doesn't collapse. That's why you keep higher pressure inside your eyeball, so even if you touch it, it doesn't collapse. So in most situations, all we talk about is the actual pressure minus the atmospheric pressure. Okay? The extra pressure is what the gauge pressure is. So again, remember, gauge pressure is actual absolute pressure minus atmospheric pressure. Okay? And so we shall use the convention, all pressures are gauge pressures unless otherwise specified. Okay? Okay, so here's an intravenous system. Okay. So we'll come to this in a second, but let me mention it here. So if you want to make fluid flow in this direction, the pressure here must be higher and the pressure here must be lower. Okay. So to make fluid flow in that direction, you have to have higher pressure in this direction here and lower pressure there. Okay, so in an intravenous fluid, in this IV system, what are you trying to do? You're trying to push this liquid into your body. Okay. What is the highest pressure that exists in your veins? That's 120 millimeters of mercury. Okay. So if you want to, so here's the needle. I'm just drawing the needle. And here the pressure is 120 millimeters of mercury. That's your blood pressure. So the pressure of the fluid at this point should be higher than 120 millimeters of mercury. And then you can push the liquid in. Right? Did you guys understand that? And that pressure at the beginning of the needle just depends on this height of the fluid. It doesn't depend on any of the shape. So the pressure in a fluid depends only on this height. Okay, so if you have a IV connection, and if you see blood coming back, blood flowing into the tube, what does that mean? This pressure was higher than that pressure. How do you fix that? You just raise the bottle. Okay? So what you're trying to do is increasing the pressure here to higher than that. Okay? All right, so how pressure depends only on the depth is found in the in the IV administration of fluid. The pressure due to the IV fluid at the entrance of the needle is proportional to the height. So at the entrance of the needle, the pressure, the IV pressure is only proportional to the height, okay? And what you want is that pressure to be higher than that for fluid to flow into the arm, okay? The shape, that doesn't matter, only this height matters, okay? Paths A and B both produce the same pressure, okay? The applied pressure can be adjusted by raising or lowering the IV bottle. So this pressure can be adjusted by raising or lowering the, okay? What happens if it's too high? This pressure is greater and you have a larger flow rate, okay? So you don't want a larger flow rate in some instances, okay? You guys understanding this? Okay. So again, the thing is, if you want fluid to flow in here, you have to have higher pressure here and lower pressure here. Okay. So let's understand this eyedropper. Okay, so let's see how the eyedropper works. I will also write down the ideal gas law. This is the pressure of the gas. That's the volume of the gas. This is the number of moles of gas. R is the gas constant, T is the temperature. Okay. Okay, now here's the eyedropper. You want to get some fluid in the eyedropper. How do you do that? We've all used these eyedropper. You first squeeze the bulb. When you squeeze the bulb, what have you done? You have removed some of the air, so you have decreased this number. Okay? Now, and then you release the bulb back again. What did you do? Now the volume has gone back to the same thing. This number was smaller, so the pressure decreased. So by removing some gas, you decrease the pressure. Okay? Initially, the pressure in this thing was 1 atmosphere. Now the pressure is lower than 1 atmosphere. Okay? The pressure was lower, and at the tip, the pressure is 1 atmosphere plus the pressure of this liquid. So the pressure is higher, the pressure is 1 atmosphere, so fluid flows in here. Okay? How high does the fluid flow? That's how low did the pressure go. Okay, so that height is now, how high does the fluid go? Now the pressure is 1 atmosphere. Okay, actually little less than 1 atmosphere. The pressure in this plus this is equal to 1 atmosphere. Okay.
So you're saying the whole, basically, eyedropper is 1 atmosphere, including the fluid part.
Okay, so I'll draw a simpler diagram. Okay, so let's say this is the eyedropper. Okay. The pressure here plus this pressure is equal to the pressure here. Okay, so pressure inside P naught is equal to the pressure inside the eyedropper plus rho GH. H is the height to which this fluid came in. Okay, the pressure at this point has to equal the pressure at that point.
So basically the whole tube.
No, the whole tube is not full. So
But aren't you including also the part, if you want to call it air, in space?
no, here on the eyedropper, this pressure, the pressure inside, the air inside is still below the atmospheric pressure. Because this pressure plus the weight of this column is equal to atmospheric pressure. Okay. All right. So, and so that's how straws work. So how do you drink from a straw? Okay, so let's, here's a straw. And so let's attach a person to the straw. Okay, so to make fluid flow from here to there, the pressure here has to be higher than there. Okay, so how do you decrease the pressure there? How do you decrease the pressure there? To decrease pressure, what you have to do is increase the volume. So when you suck on it, you're decreasing the pressure there, okay, and fluid rises. Okay. So when you remove air from the straw, you're decreasing the pressure here, and fluid flows from here to there and flows up there. Okay, so that's how you drink from a straw. So for instance, okay, if a straw was 10 meters long, if a straw was 33 feet long, even if you remove all the air, water would only rise up to 33 feet. So you couldn't drink from a straw longer than 33 feet, even if you removed all the air. Okay. All right. Now we'll study something called the Pascal's law. Okay. So this is the kind of this is this law is used in a dentist chair. Okay, what Mr. Pascal discovered is the following. Okay, so here's an enclosed fluid. So here's a fluid that's enclosed. Okay, and you saw that the pressure there. So the pressure on the fluid here is 1 atmosphere, and as you go deeper in the fluid, the pressure increases. If you went, for instance, 33 feet deep, the pressure would be 2 atmospheres, and so on. Okay. Now what we'll do is we'll enclose this fluid. We'll put a piston on top of it. Okay. And let's say you push on this fluid. So what did you do? You increase the pressure at this point. Okay. So let's say you increase the pressure by 0.2 atmospheres there. Okay. What Mr. Pascal realized was if you increase the pressure at one point by 0.2 atmosphere, at every point you've increased the pressure by 0.2 atmospheres. Okay. So if you increase the pressure by a certain amount in an enclosed fluid, that pressure is increased, that increase is transmitted everywhere in the fluid. All right, so let's see the consequence of that. Well, the pressure here increased by 0.2 atmosphere. So the pressure here increased by 0.2 atmosphere. And that's what this is saying. So you increase the pressure by 0.2 atmosphere here, and the same increase happened at that point. All right, well, what is the big deal here? Here's the big deal. Okay, so let's F1 over A1 was the increase in pressure at 0.1. That is equal to the increase in pressure everywhere, but that's the increase in pressure at this point as well. So when you push down on it, the push up here, let's see what that is equal to. So F2 equal to A2 divided by A1 times F1. All right, so, well, what did this do? This is the output force, okay? So if A2 is greater than A1 by a factor of 10, so if this area is 10 times this area, then the output force is 10 times the input force. Okay? And that's not hard to do. So if this area is 10 times that, the output force is 10 times the input force. You push down with a force of 10 pounds, and you can lift up 100 pounds. You got a force multiplier. Okay, that's how cars are lifted in a mechanic shop. Okay, so this is a hydraulic lift. You press down, you push with a small force, and you lift a heavy object. Okay. When you're sitting on a dentist chair, the dentist has this foot pedal. He's pushing down on this piston, and the patient in the chair is being lifted by that piston. Okay. Did you guys understand that? So this is a force multiplier. What is the price you pay? You have, this piston has to move a long distance for this to move a little distance. Okay. So if this factor is 10, if you get a force multiplication of a factor of 10, this piston has to move 10 times as far as this piston moves. Okay. All right, so this is the Pascal's principle. Okay, so here's this is the dentist problem that I talked about. Okay, so calculate the force the dentist must exert if the patient plus chair has a mass of 120 kgs. So most of our mass is about 60 kgs here. So place, the chair weighs almost as much as a person. Okay, and this is a diameter of 1 centimeter, which is half an inch, and this diameter is is 5 centimeters, which is 2 inches. Okay, so the area of a circle is pi r square. Okay, so if the radius is 5 times, this radius is 5 times greater than this radius, the area is 25 times greater. This area is 25 times greater than that. So going back to this is 25 times greater than this. So if the input force is 1 pound, the output force is 25 pounds. You're getting a multiplication factor of 25. Okay? That's what's happening in the dentist chair. Did you guys understand that? Okay. So that's the calculation. So there's here what they're asking you is the output force. You're lifting a 120 kg person, and so that's the output force. What is the force that the dentist is applying? That's what's being calculated. So the output force is in newtons is mass times gravity. It's mass times gravity. There is the output force. And they calculate the area. So the input force is, by the way, here's a typo. Again, the input force, there's the input area divided by the output area. The input force is 15 newtons, about 15 newtons. And the output force was what you lifted was this much, about 1200 newtons. So applying a small force, you lifted a large weight. Okay. Okay. So again, this device is a force multiplier. Okay. So anytime you want to do heavy lifting with a hydraulic lift, you press down on the small cylinder and you're lifting a heavy object on the big cylinder. Okay. And again, this is all based on Pascal's principle. What does Mr. Pascal say? That in an enclosed fluid, any increase in pressure is transmitted undiminished throughout the fluid. Okay? You increase the pressure by a certain amount at one point in a fluid, that is transmitted throughout the fluid. Okay? All right, so now let's come to blood pressure measurements. Okay, so what you want to do is measure the pressure of the blood that's coming out of the heart. Okay, so again, you saw that what is 1 atmospheric pressure? It's the weight of the column of air all the way to space. And if you're in a fluid, it depends on the depth of the fluid as well. Okay, so the pressure at this point is atmospheric pressure plus rho GH, where H is the height of this fluid. Okay, so when they measure your blood pressure, you want to put the cuff right at heart level. Okay, so then you get the pressure at the heart. Okay, so if you put the cuff here, then the pressure will be at the heart plus the height of this column of liquid. Okay, so you put the cuff right at the level of your heart. In blood pressure measurements, an inflatable cuff is placed on the upper arm at the same elevation as the heart. Okay, if you put it lower than the heart, then you get a higher pressure, and if you put higher than the heart, you get a lower pressure. Okay, and inflated until blood flow is cut off in the brachial artery. So what are you doing? So the blood pressure inside the blood vessel, if you apply a greater pressure than the blood pressure here, then the artery collapses and the blood flow stops. Okay, so if this pressure is greater than the blood pressure, the artery collapses, okay? And no flow is there, okay? So now you first make the artery collapse, and then you decrease this pressure, and the blood vessel opens up. When flow starts again, that's the highest pressure. Okay? When the applied pressure exceeds the heart's maximum output pressure, the artery collapses. Okay? The person making the measurement slowly releases air from the cuff, lowering its pressure, and listens for flow to resume. When pressure in the cuff becomes lower than the maximum heart's output, the artery opens up and flow resumes. Okay, and that's how you measure the highest pressure, and that's called the systolic pressure. Okay. And the diastolic pressure is the minimum pressure. When the pressure decreases below the minimum pressure, the artery is fully open, and you can hear the difference. Okay, so now the artery is fully open, and this so the sound is different. So diastolic pressure is minimum pressure the circulatory system experiences and can be detected as the change in the sound of blood flow through the unrestricted. Okay, so before the pressure decreased below the diastolic pressure, the artery was restricted, and when it reduces to below the diastolic pressure, it's unrestricted. Okay, so it's fully open. Okay. So that's how blood pressure is measured. Okay, spinal column pressure. There's fluid in your spinal column, and okay, and this fluid is actually connected to a fluid in your brain, so it's called the cerebrospinal fluid. And to make sure that everything is flowing properly, you can measure the pressure at this point. Okay, and we'll talk about this in the next chapter. So so the pressure, if something gets blocked, the fluid in the brain will not be connected to the spinal fluid, and that's a problem. And so they measure this pressure. Okay. Now, when you do a spinal tap, does anybody has done this in this room? You've done a spinal? You've had one, or you do one?
I've had one.
Okay. All right, so when you measure blood pressure, okay, so what you're doing is you're pumping air. Air doesn't weigh too much, so this gauge can be anywhere. Won't matter whether you're holding the gauge here or there. Okay, the location of the gauge doesn't matter. But when you're doing a spinal tap, what you're doing is you're using a saline solution. Okay, and so the weight of the saline solution matters. So when you're doing a spinal tap, you're trying to if you want to measure the pressure here, the gauge has to be right at that level. If the gauge is at this level, then the weight of this height of saline will come into play. Okay, or when you're at this height, so if the gauge is below, then you're getting a higher pressure reading. Here you're getting a lower pressure reading. Okay, so in the spinal tap, you have to be careful because the weight of this saline solution will matter. Okay. So that's why you're measuring the pressure here. Again, like I said, it's called the cerebrospinal fluid because this fluid is connected to your fluid in around your brain, and there are little channels that can get blocked, and then that pressure is not transmitted to this pressure, and so you'd get a lower pressure. Okay, so again, all these pressure measurements are indicative of if something has gone wrong. Okay, so that's why you want to measure. Okay, So in spinal column pressure measurement, a liquid rather than a gas is used to transmit pressure to a gauge. A long needle is inserted between the vertebrae into the spinal column fluid, and pressure is transmitted to the gauge via sterile saline solution. So that's a saline solution. Okay. To obtain an accurate reading, the gauge must be placed at the same vertical height as the needle. Okay, so this guy is measuring pressure at this point. This would give you a lower pressure, and this would give you a higher pressure. Okay. Okay, so you will come across these two words, manometers and a barometer. Okay, a manometer is what's used to measure blood pressure, and a manometer gives you it gives you the gauge pressure. It gives you the actual pressure minus the atmospheric pressure. A barometer gives you the actual pressure. Okay. So here's a manometer. So this is open to the atmosphere, okay, and this is going to the cuff. So that cuff that's measuring that's going to the cuff, okay. So that's the pressure around your arms that's being measured, okay, and that's where you're measuring the blood pressure, okay. So there's the pressure on the cuff, and there's atmospheric pressure. So when you're measuring 120 millimeters of mercury, that's the 120 millimeters of mercury. See, its blood pressure is about 120 millimeters of mercury. Okay, so the pressure is greater than the atmospheric pressure by 120 millimeters of mercury. Okay, and that's so the actual pressure at this location would be 760 plus 120 millimeters of mercury. 880 millimeters of mercury. Okay, so again, all the pressures, the blood pressures that you hear are gauge pressures. Okay, they're the actual pressure minus atmospheric pressure. Okay, so a single tube manometer filled with mercury is commonly used in blood pressure measurements. Okay, that's how it looks. Typical blood pressure measurements produce values of H ranging from 8 to 300 millimeters of mercury. Okay, I've never heard that low a pressure. Okay. You have low You have that low pressure, you probably faint, right? Or die. Okay. So a healthy blood pressure is 120 over 80 means systolic pressure is 120 millimeters of mercury, and diastolic pressure is 800 millimeters of mercury. Okay, so a barometer measures the actual pressure. Okay, so what a barometer does is, okay, so here's a barometer. You might have seen this in your chemistry lab. Here, this is a perfect vacuum. So there's no air there. Okay. So in a barometer, what is happening is this column of mercury is balancing an equal column of air all the way to space. Okay. The weight of this is balancing this air. Okay. So to make a barometer, what you do is you take a tube, fill it with mercury, and then put your thumb across it, and then invert it and place it in a mercury bath. And so the mercury column will rise, and there'll be no air there. That'll be perfect vacuum. Okay. So anyway, there's a barometer. So this column of mercury is being balanced by this column of air of equal area. Now, what this diagram is illustrating is the shape of the barometer doesn't matter. So 1 atmosphere is equal to the height of this column of mercury. Okay? And the shape of this doesn't matter. What matters is this height. Okay? And again, 1 atmosphere will balance 760 millimeters of mercury. That's 0.76 meters of mercury. And of course, if you go to higher altitudes, you're supporting less air, and so that pressure decreases. Atmospheric pressure varies with altitude and weather conditions. So commercial airlines fly at about a height of 11 kilometers. And there, the pressure is about 20% atmospheric pressure. Okay? And that air is too thin, so that's why you have to pressurize air cabins. An aneurysm is a blood vessel wall has weakened and it's become a little balloon. Okay. Now, you saw that pressure is force divided by area. Okay, so we'll talk about so what is the problem with this? Okay, so force is pressure times area. Okay. So here was the blood vessels. Here is the healthy blood vessel, and now an aneurysm has developed, and this has become a balloon. Now let's see what is happening. Okay, so let's say the pressure is the same. If the pressure is the same, but now the area of this balloon has increased, the area is increased. So the force on this balloon is increased. Okay, so this wall, it became a balloon because it was weak to begin with. And now if the pressure is the same, the force has increased, and so the problem is going to get worse. Did you guys understand that? All right, so let's calculate how much force there will be on this balloon. Okay, so calculate the maximum force in newtons exerted by the blood on an aneurysm or ballooning in the aorta, given the maximum pressure is 140 millimeters of mercury. So this is a slightly higher pressure. And the area in the aneurysm is 25 centimeters square. Okay, so 3 is 4 pi r squared. All right. So this aneurysm is about an inch across. Okay. Now, 25 centimeters, 4 pi 12 to roughly half an inch across. Okay. All right. So the force would be the pressure is force divided by area. The pressure is 140 millimeters of mercury. Remember, this is gauge pressure. Okay. Well, okay. Gauge pressure is all we need. So, okay. So this is that's 140 millimeters of mercury. So the pressure is density of mercury times G times height. Okay, this is the density of mercury is that. There is G, and there's the height in meters. Okay, so there's the pressure converted to Newton per meter square. Okay, so it's converted to pascals. And this is the area. We are going to convert that to meter square, which is that conversion. Okay. And so the force is pressure times area. There's the pressure times the area, and that's 50 newtons. Okay, so the force on this aneurysm now, so your weight is about 500 newtons. That's 1/10 your body weight. That's an enormous force. Okay, and so this wall is already weakened, and because the area increases, the force has increased. Okay, so this is a large force for the blood vessel to withstand, and there's considerable risk that the aneurysm will burst. Okay? And this happens inside your brain. That's if a blood vessel bursts inside your brain, that's bad news. Okay, so you want to keep your blood pressure within acceptable limits. Okay. Did you guys understand that? Okay, so when the area increases, the force increases. Okay. All right. So you saw that in a fluid, here the pressure is atmospheric pressure, and as you go deeper, the pressure increases. So let's look at this bubble here. The pressure at the top, so this could be an object, the pressure at the top is lower than the pressure at the bottom. So when you immerse an object in a fluid, since the pressure at the top is lower than the pressure at the bottom, there's a net upward force on you when you immerse an object in a fluid. In fact, if you don't panic, I guess, so if this is you underwater, because the pressure here is lower, okay, than here, there's a net upward force on you. Okay, so there's a net upward force on you, and this upward force is equal to your weight. So if you're underwater, you're weightless. Okay, essentially. So you wouldn't sink, almost. Okay, so if you don't panic. All right, this upward force exerted by the fluid is called the buoyant force. Okay, so whenever, what we are saying is a buoyant force is whenever you immerse an object in a fluid, you feel a upward force, which is called the buoyant force. And Mr. Archimedes told us exactly how much this buoyant force will be, how large this buoyant force will be. Mr. Archimedes realized that this buoyant force is equal to the weight of the fluid displaced. Okay, so if you displace 10 pounds of fluid, then the buoyant force is 10 pounds on you. If you displace 50 pounds of fluid, the buoyant force is 50 pounds on you. Okay. So the buoyant force on you is equal to the weight of the fluid displaced. Okay. So buoyant force is the result of increasing pressure with depth. It can exist only in gravitational fields. So if you were out in space, far away from any object, you wouldn't have buoyant forces. Okay. Mr. Archimedes realized how large the buoyant force will be. There's the buoyant force. This buoyant force, the buoyant force is equal to the weight of the fluid displaced by the object. Okay. So, and there's the fluid density. This is the weight of the fluid displayed. There's the fluid distance. Okay, so the apparent weight of an object in a fluid is the actual weight minus the buoyant force. So the weight, now if you weight this object, it will be the actual weight of the object minus the buoyant force. Okay. So I guess, so here's the bathroom scale. You stand on the bathroom scale and you get your weight. Now if you do the same experiment underwater inside a pool, your weight would be your actual weight minus the buoyant force. Okay, and our density is essentially the density of water. So if you weighed yourself underwater inside a pool, you'd weigh nothing. Okay, you'd weigh zero. Okay, when an object floats, its density, the density of the object has to be less than the density of the fluid. That's only when it can float. Okay, so the density of the object divided by the density of the fluid is equal to the volume displaced. Volume displaced is the volume underwater, and divided by the volume of the object. Okay, so when an object is floating, the displaced volume is less than the volume of the object. This number is less than 1, and so the object density has to be less than the density of the fluid. that's only when it can float. Okay? By the way, the density of ice is 90% the density of water. So in an iceberg, 90% of the iceberg is underwater. Okay? Now all captains know this. This is common knowledge, and the Titanic captain still ran into an iceberg. Okay? You don't know what's underwater. Okay? What's the shape of the iceberg? Okay? All right. So we'll be interested in making fluids flow. Your circulatory system makes blood flow through your body. Okay. So we'll be interested in making fluids flow through a tube. Okay. Again, to make a fluid flow, you have to have a high pressure here, low pressure there. Okay. And the flow rate is, let's say, how many gallons a minute are flowing and so on. Okay, that's the flow rate. The flow rate is the difference in pressure. Delta P means the difference in pressure across the tube. Okay. Divided by the resistance to the flow. Resistance arises from friction. For instance, the fluid will have friction. There'll be friction against the walls and so on. Okay. And the resistance to flow will depend on the radius of the pipe and all that. Okay, so for instance, so let's make sure we understand this. So let's say this is a pipe and there's water flowing, and there's an exactly similar pipe with honey flowing. We'll maintain the same pressure difference. What will flow at a greater rate, water or honey? Water, of course. Okay, that means honey has a greater resistance. Okay, the resistance depends on something called the viscosity of the fluid. Honey has greater viscosity. So the resistance depends on the viscosity, depends on the length of the tube and the radius of the tube. Okay, so let's make sure we understand one fact and then we'll end. Okay. Okay. If you want to increase the flow rate, you want to decrease the resistance. Okay. Maintaining the pressure difference, if you maintain the same pressure difference, to increase flow rate, you want to decrease the resistance. Okay. So I'm going to go over an example. We'll come back to this in a minute, okay? I mean, next time as well. So when a person eats a large meal, okay, the body wants to increase the flow rate from 1 liter a minute to 5 liters a minute. Okay, you want to increase the flow rate of blood to your digestive system by a factor of 5. Why do you want to do that? Well, you ate a meal and you want to absorb all the nutrients. How do you increase the flow rate by a factor of 5? What's that? Yeah. So you want to decrease this by a factor of 5. Okay. You want to decrease the resistance by a factor of 5. And the easiest way to do that is, okay, increase the radius of the blood vessel, dilate the blood vessel, and decrease the resistance. Okay. So that's what this problem tells you. Okay. So to increase, so you dilate the blood vessel by a factor of 50%. Okay, so if the blood vessel was 1 inch in diameter, you make it 1.5 inch in diameter. Okay. So we see that if the radius is increased to 1.5 of its original size, the flow rate will be 5 times its original value. Okay, so that's how you control flow rate in your body. And if you exercise and you want to cool down, what you have to do, you have to sweat more. And so what you want to do is increase blood flow to your skin. So you dilate your blood vessels to the skin. Okay? You want to increase flow rate to your muscles to provide oxygen and nutrients and stuff like that. You dilate your blood vessels. When you're cold, you don't want to lose heat. You don't want, so what you want to do, you want to cut down blood flow to your skin. You constrict your blood vessels. Okay. So again, so this is flow rate. That's the pressure difference. If you want to increase flow rate by 5 and increase this pressure difference by 5, your heart is having to work much harder, and your heart can't work that hard. Okay. So what you want to do is control the resistance. Okay. Again, resistance is eta is the viscosity that depends on the fluid. That's the length of the tube. R is the radius of the tube. Okay. And so that's what you want to control because that has the greatest effect. All right. All right, guys, we'll stop here and we will start back at this point next week.